Here are 11 probability questions that keep getting more difficult. Make sure to try the question before watching the solution, and then let me know in the comments how many out of 11 you were able to get. Level 1. When rolling a 6-sided die, what is the probability of rolling a 3? For this question, we just need the general theoretical probability formula, which says the probability of event A happening equals the number of ways event A can happen, which we call the event space, and divide that by the total number of possible outcomes, which we call the sample space. So to find the probability of rolling a 3 on a standard 6-sided die, I need to know how many of the outcomes on a 6-sided die are a 3, and divide that by the total number of possible outcomes on a 6-sided die. While on a 6-sided die, only one of the outcomes is a 3, and there are 6 total outcomes that you could get when rolling a 6-sided die. So the probability of rolling a 3 is 1 out of 6. And any probability could be expressed as a fraction, or as a decimal, or as a percentage. Level 2. If you flip a coin, and then roll a 6-sided die, what is the probability of flipping tails and rolling a 2? For this question, the word "and" tells me that I want the probability of 2 events happening in sequence. So I'm going to need to use the multiplication law for independent events. And these events are independent because flipping tails on the coin does not affect your probability of rolling a 2 on the die. So the formula we'll use, if you want the probability of event A happening and then event B happening, because the events are independent, you just do the probability of event A happening and then multiply that by the probability of event B happening. In probability, it's usually safe to associate "and" with multiplication. So for this question, we want the probability of flipping tails and then rolling a 2. So I'll need to multiply the probability of flipping tails with the probability of rolling a 2. So the probability of flipping tails, well, one of the 2 sides of a coin are tails, so that probability is 1 out of 2. And that gets multiplied by the probability of rolling a 2. Well, one of the 6 sides of a standard die is a 2, so that probability is 1 over 6. And when we multiply those probabilities together, we get 1 out of 12. Level 3. When rolling a pair of 6-sided dice, what is the probability of rolling a sum of 7? The theoretical probability formula would tell me that if I want the probability of rolling a sum of 7, I would need to know the number of ways that I could roll a sum of 7, and divide that by the total number of possible outcomes I can get when I roll a pair of 6-sided dice. Well, when I roll a pair of 6-sided dice, let's say one of the dice is red and one of them is green. There are 6 options for what can show up on the red die, and 6 options for what can show up on the green die. So multiplying the number of options for each die together tells me that there are 36 different possible outcomes that can happen when I roll the pair of dice. So I know the number of elements in my sample space is 36. But how many of those 36 outcomes are a sum of 7? You could roll a sum of 7 by rolling a 6 and a 1, or a 1 and a 6, a 5 and a 2, or a 2 and a 5, or a 4 and a 3, or a 3 and a 4. So there are 6 total outcomes that are a sum of 7. So the probability of rolling a sum of 7 is 6 out of 36, which reduces to 1 out of 6. Level 4. If you draw a card from a standard deck of 52 playing cards, what is the probability that the card is a heart or a face card? Now, in a deck of cards, there are 13 hearts and 12 face cards, right? The face cards are the Jack, Queen, and King. So there are 3 face cards for each of the 4 suits, meaning 12 face cards. What we want is the probability that if you draw a single card, you get a heart or a face card. That word "or" tells me that I want the probability of the union of 2 sets. The formula for the union of 2 sets, if I want the probability that event A or event B happens, what I can do is do the probability of event A happening plus the probability of event B happening. Now, if the events are not mutually exclusive, like these events, we also have to subtract the probability that they both happen, that event A and event B both happen. For this question, when we draw a card, it is possible for the card to be both a heart and a face card, which is why we need this part of the formula. So if I apply this formula to this question, where I find the probability of drawing a heart or a face card, I would have to do the probability of drawing a heart plus the probability of drawing a face card, and then subtract the probability that the card is both a heart and a face card. Well, the probability that a card is a heart, 13 of the 52 cards are a heart, plus the probability of a face card, well, 12 of the 52 cards are face cards, but I then have to subtract the probabilities that have been double counted, right? There are some cards that have been double counted in this 13 plus 12. How many cards are both a heart and a face card? Well, there are 3 face cards that are hearts, the Jack, Queen, and King of Hearts. So I have to subtract the probability of drawing one of those 3 cards that were double counted when we added these probabilities. And that would probably make even more sense if I draw a quick Venn diagram of those sets. Now, if I were to just do the probability of a heart plus the probability of a face card, I would be adding the number of hearts with the number of face cards. So I would be doing all 13 of these cards plus all 12 of these cards. And notice these 3 cards that are both a heart and a face card were double counted, which is why we then have to subtract the probability we get one of those cards that was double counted. And when simplifying this, 13 plus 12 minus 3 is 22. So the probability of drawing a heart or a face card is 22 out of 52. And looking at the Venn diagram, notice adding these 3 numbers together is 22, which is why that's the probability of drawing a heart or a face card. And we could, of course, simplify that probability. We could simplify that to 11 out of 26. Level 5. What is the probability of being dealt 2 clubs in a row from a well-shuffled deck of 52 cards without replacing the first card drawn? So for this question, we want to draw 2 clubs in a row, which means I want to find the probability that the first card I draw is a club and the second card I draw is a club. For probabilities, when we want one event to happen and another event to happen, we're going to use multiplication. But for this question, I'm going to need the formula for the multiplication of dependent events. I know these events are dependent because I'm not replacing the first card that's drawn. Meaning, after you draw the first club, that's going to affect the probability of you drawing the second club. So the formula for the probability of event A and event B happening, if the events are dependent, we do the probability of A and multiply that by the probability of B happening, given that A has already occurred. So for this question, I need to do the probability that the first card drawn is a club, and multiply that by the probability that the second card drawn is a club, given that the first card was a club. Well, the probability that the first card you draw is a club, 13 of the 52 cards are clubs, and then we have to multiply that by the probability the second card is a club, given that the first card was a club. So we've already drawn a card out of the deck of cards, meaning there are only 51 cards left to draw from. And how many of those 51 cards are clubs? Well, we're given that the first card drawn was a club, meaning there are no longer 13 clubs left in the deck. We've taken one of those out. So there are only 12 clubs left in the deck. And then if I multiply these probabilities together, I get 156 divided by 2,652. And that could be written as a decimal, as 0.0588, or about a 5.88% chance of drawing 2 clubs in a row from a standard deck of 52 cards. Level 6. If you roll a pair of dice until you get a pair or doubles, what is the probability it takes you less than 4 tries? Now this question is a geometric probability distribution question, and because it's about the number of tries until your first success, where in this question, a success is rolling doubles. The formula for a geometric probability distribution looks like this. where K stands for the trial number that is the first success. 1 minus P is the probability of failure, P is the probability of success, and K minus 1 would just be your number of failures. So for this question, if we want the probability of, we call it the waiting time, how long do we have to wait for the first success? The probability that the waiting time is less than 4, we could break that up into the waiting time being either 1, 2, or 3 trials. And notice I said or, which is why I am adding the probabilities of each of those options. So I can just use this formula 3 times. And before I do that, it'd probably be helpful for me to write down what the probability of getting doubles is. Well, when rolling a pair of 6-sided dice, there are 36 different outcomes that you could get, and of those 36 outcomes, 6 of them are doubles. So you have a 6 out of 36, or 1 out of 6 chance of rolling doubles when you roll a pair of dice. So this is going to be our probability of success each time we use the formula. And the probability of failure would be 1 minus that probability, which is 5 out of 6. So if I want the probability of the first success being on the first trial, that would mean that I would have to fail 0 times and then succeed. And then the probability of having to wait 2 tries to get your first success, that would mean we would have to fail 1 time and then succeed. And the probability of having to wait 3 tries to have your first success of rolling doubles, that would mean that you would have to fail on your first 2 attempts, so probably a failure to the exponent of 2, and then have a success. If I evaluate that probability, I get about 0.4213, which means there's about a 42.13% chance of getting doubles in less than 4 tries. Level 7. In a group of 10 people that have 6 adults and 4 children, if you were to choose 4 people randomly, what is the probability there are an equal number of adults and children? Well, for this question, if I'm making a group of 4 people and I want an equal number of adults and children, that means in my group, there's going to be 2 adults and 2 children. So I want to find the probability that in my group, I have 2 adults and 2 children. So to find that probability, I would have to know the total number of groups I could make that have 2 adults and 2 children, and then divide that by the total number of groups that I could make from all 10 people. Now for this question, we're making groups of people where the order within the groups does not matter. So we'll need the combinations formula for this question. When finding the number of groups of people you can make, that's called finding the number of combinations of n items taken r at a time, which can be written like that, or it can be written like this as n choose r. And the formula tells us that we would do n factorial divided by n minus r factorial times r factorial. So I'll shrink this formula, move it off to the side, and let's go ahead and try and do this question. Now I have to find the number of groups that have 2 adults and 2 children. So in making a group that has 2 adults and 2 children, from the 6 adults, I have to choose 2 of them. And the combinations formula will tell me how many different ways that can happen. And similarly, from the 4 children, I have to choose 2 of them. And that gets divided by the total number of possible groups I could make. So from all 10 people available, how many different groups of 4 can you make? Doing 10 choose 4 would calculate that. And when I evaluate each of those combinations, let me actually just show you how this one simplifies. When doing 6 choose 2, it would end up simplifying to 6 times 5 divided by 2 factorial. When we're choosing 2 adults from the 6, you have 6 choices for your first adult and then 5 choices for your second adult. And then we have to divide by 2 factorial, because for each of these groups that are made, we could rearrange the people in that group 2 factorial ways, and it's still the same 2 people. So this would simplify to 15 times 6 divided by 210 total possible different groups that could be made. So we have a probability of 90 over 210, which reduces to 3 out of 7, or as a decimal, that's about 0.4286. Level 8. A multiple choice quiz has 10 questions. Each question has 4 possible answers. If you guess the answer to all the questions, what is the probability you get at least 3 correct? So we want the probability of at least 3 successes out of 10 trials. And each of the trials are independent of each other, which means the probability of success on each trial is constant. For each question, you have a 1 out of 4 chance of guessing the correct answer. All of those conditions means we have a binomial probability distribution. And the formula for a binomial probability distribution looks like this. The probability that your number of successes equals k equals n choose k times the probability of success to the exponent of the number of successes times the probability of failure to the exponent of the number of failures. And for this question, we'll have to use this formula a bunch of times. Well, what are the different options for the number of questions you could get right on this 10 question test? You could get anywhere from 0 to 10 correct answers. We want the probability of at least 3 correct. So what we would want is the probability of all of those possibilities added together. But since I know that if I were to add the probabilities of all 11 of these outcomes together, it would equal 1. Meaning, I could do 1 minus the probability of getting 0, 1, or 2 successes, and that would give me the probability of getting 3 or more successes. So that's what we'll do. The probability of the number of successes being greater than or equal to 3 would be equal to 1 minus the probability that the number of successes is less than 3. And the number of successes would be less than 3 if I had either 0 or 1 or 2 successes out of all 10 of my trials. So let's calculate those. If I'm going to have no successes, that means I'm going to guess the wrong answer to all 10 questions. And the probability of guessing the wrong answer is 3 out of 4, right? 3 of the 4 possible options on any multiple choice question are wrong. So you have a 3 out of 4 chance of guessing wrong. And I need to guess wrong 10 times. So I would have to do 3 out of 4 to the power of 10 to figure out the probability of that happening. If I use my binomial distribution formula, I could add these 2 components of it, and it's not going to affect the probability. My probability of success is 1 out of 4, but I'm going to be successful 0 times. And then I multiply that by n choose k, which means how many different ways from the 10 questions can I choose none of them to be correct? Both of these just equal 1, so they don't affect the probability. Plus, let's now calculate the probability of having 1 success. I would have to do 10 choose 1. That would tell me the number of different ways I could choose one of the 10 questions to be the success, times the probability of success to the power of 1, times the probability of failure to the exponent of the number of failures I want to have. If I'm going to have 1 success, that means I'm going to have 9 failures. I'm going to get the answer wrong on 9 of the questions and the answer right on 1 of them. Plus, lastly, the probability of getting 2 questions correct. 10 choose 2 will tell me how many different ways I can choose 2 of the 10 questions to be the correct questions. The probability of success to the exponent of the number of successes times the probability of failure to the exponent of the number of failures. If I'm going to be successful 2 times out of 10 tries, that means I'm going to fail 8 times. If I were to evaluate inside the square brackets here to find the probability of having less than 3 successes, I would get about 0.5256, which means that if we do the subtraction, there's about a 47.44% chance that you get greater than or equal to 3 of the questions correct. Level 9. In a class of 23 students, what is the probability that at least 2 students share a birthday? This is a classic probability question often referred to as the birthday paradox. And it's a paradox because most people would think of the probability as being fairly unlikely to happen. But let's calculate it. Now, since there are so many different ways that at least 2 students could share a birthday, it would be a lot easier to find the probability that no 2 students share a birthday. And then using that answer, we could find the complement of that, which would be at least 2 having a birthday. by doing 1 minus the probability that no two people share. Now let's start up here by finding the probability that no two students share a birthday. So we'll think of all 23 students one at a time. We'll find each of their probabilities of having a unique birthday and multiply them together. The probability that the first student has a unique birthday, there are 365 days they can choose from out of the 365 days, and they'll have their own unique birthday because there's no one yet we're comparing to. We need to multiply that by. Now, student number 2 can't share a birthday with the first student, which means there are only 364 days left for them to choose from out of the 365 days in a year. Oh, and I forgot to mention, we're going to ignore leap years in this. We'll assume all years have exactly 365 days. And then moving on to student number 3, they can't share a birthday with student number 2 or student number 1, which means there are only 363 days left they can choose from of the 365 days. And you can see how this pattern would go. This is going to keep going until we get all the way down to student number 23. They're not going to be allowed to share a birthday with any of the previous 22 students, which means subtracting 22 from 365, there would be only 343 of the 365 days left that the student could choose from to still have a unique birthday. Now, all of this multiplication, typing all of that in, would be pretty tedious. We can simplify this a little bit. Notice the denominators of each fraction are 365, and there's going to be 23 fractions being multiplied together. So the denominator could just be rewritten as 365 to the power of 23. And in the numerator, I've got 365 times 364 times 363 all the way down to times 343. What's happening with that? I'm basically finding the number of different ordered arrangements of 23 numbers I can make from a group of 365 numbers. Another word for ordered arrangements is permutations. So I'm finding how many different permutations of 365 objects taken 23 at a time I can make. And let me make a bit of room and we'll write down what that calculation would result in. That calculation would be approximately 0.4927. That means there's about a 49.27% chance that no two students share a birthday. So if I wanted to find the probability that at least two share a birthday, that's just the complement of that probability. So I would just do 1 minus 0.4927, which is about 0.5073. Which means there is more than a 50% chance that at least two people share a birthday in a class of 23 students. Level 10. Estimates suggest that 1 in every 250 people, so 0.4% of people, has been infected with a certain disease. Tests that are given to detect the disease in people are 99.5% accurate. Chris is randomly selected to test if he has the disease, and his test is positive. What is the chance that Chris has the disease? Now, the answer to this question is actually a little bit counterintuitive. To understand what's going on in this scenario, let me draw a tree diagram. Now, a randomly selected person either has the disease or they don't have the disease. And then no matter whether the person has the disease or does not have the disease, the test is either going to be positive or negative. And now let me fill in some probabilities. There's only a 0.4% chance that a randomly selected person has the disease. So as a decimal, if I divide that by 100, that's 0.004, which means the probability that they do not have the disease would be the complement of that, which I could calculate by doing 1 minus that probability, which is 0.996. Now, if the person has the disease, a correct test result would be them testing positive. And since the test is 99.5% accurate, the probability of that happening is 0.995, which means the probability that you get the wrong test result if the person has the disease would be 1 minus 0.995, which is 0.005, a 0.5% chance. And if they do not have the disease, a correct result would be a negative test result, and the test will be correct 99.5% of the time, and incorrect 0.5% of the time, so 0.005. If we follow the branches of the tree diagram, there's 4 different scenarios for what could happen if we have a randomly selected person from the population. They could have the disease and then test positive, which is a correct test result, so we call that a true positive. And we could find the probability of that happening just by multiplying the probabilities along that path. So 0.004 times 0.995 is 0.00398. They could have the disease and then test negative, which would be an incorrect test result, so we would call that a false negative. And the probability of that happening would be 0.004 times 0.005, which is a very small probability, 0.00002. They could not have the disease, but incorrectly test positive. Since that would be an incorrect test result, we would call that a false positive. And that probability would be 0.996 times 0.005, which is 0.00498. And the last scenario, not having the disease and correctly testing negative, is the most likely event. It's 0.99102. Now this question says we're given the test is positive. We know for sure it's either a true positive or a false positive. But of those two that we know it's between, what's the probability he has the disease? So what's the probability that it's the true positive and not the false positive? So we can just use a conditional probability formula. We would find the probability that he has the disease given he has a positive test result. To do that calculation, we would do the probability that he has the disease and got a positive test result, and then divide that by the probability of what's given. We're given that he tested positive, so divide it by the probability that he tested positive. And then just looking at the tree diagram, we can get both of these probabilities. The probability that he has the disease and tested positive, has disease and test positive, that's this probability right here. And then the probability that he tests positive, well, there are 2 different positive tests, a true positive or a false positive. So the total probability of testing positive would be the sum of these 2 numbers, which is 0.00896. And if we divide those 2 numbers, we get the probability that Chris has the disease to be 0.4442. Level 11. If the 11 questions on this video were randomly ordered, what is the probability that the easiest and hardest question will be beside each other? To find the probability that the easiest and hardest are beside each other, I would need to do the number of arrangements where they're beside each other, and then divide that by the total number of possible arrangements of the questions. Well, the number of arrangements of 11 questions is easy. It's just 11 factorial. But how many of those 11 factorial arrangements have the easiest and hardest beside each other? So if question 1 is the easiest and question 11 is the hardest, if I were to make an arrangement with 1 and 11 beside each other, notice that all the different arrangements I make where they're beside each other, they're always moving together. So we can think of question 1 and 11, you can think of them as a single question. You can group them together. So instead of having 11 items to arrange, we really only have 10 items that we're arranging if we're always keeping 1 and 11 together. So the number of arrangements that have 1 and 11 beside each other would be 10 factorial. But in each of those arrangements where 1 and 11 are beside each other, we could change the order of the 1 and the 11. Instead of it being 1 then 11, it could be 11 then 1. So to get the true number of arrangements that have the easiest and hardest beside each other, I have to multiply this by the number of ways I could rearrange the 2 questions that are stuck together. How many ways can we rearrange 2 items? Just do 2 factorial, which is just 2, which means there's 2 ways. Either 1 and 11 or 11 then 1. And then if we do this calculation, we get about 0.1818. So there's about an 18% chance that they'd be beside each other. So there you go. That's all 11 probability questions. Let me know in the comments which ones you found difficult, how well you did, and what you want a video on next. Jensen Math!